at the height he gets on this football. He's going to throw it straight up in the air. And as a receiver, what happens is it comes straight down. So even though the
Projectile motion, the math that got the Seahawks to the playoffs. The Russell Wilson and Tyler Lockett pass, an example of projectile motion. Projectile motion is a branch of classical mechanics in which the motion of an object is analyzed under the influence of the constant acceleration of gravity, whether or not it has been propelled with some initial velocity. Here is the problem I'm going to solve. H equals negative 16t squared plus 79.15t plus 6. My example problem will model projectile motion with initial velocity using Russell Wilson's throw to Tyler Lockett against the Chiefs on December 23, 2018. Projectile motion is shown by a quadratic formula, h equals at squared plus bt plus c. To solve this equation, the only variable we know is the acceleration constant, which in feet per second is negative 16. Knowing this, we had to find out the initial velocity and the initial height. For initial velocity, using the video, we had to measure two things, the projection angle and the range. I found the projection angle by measuring the angle between Russell Wilson and the ball in the air traveling towards the vertex. We found that Russell Wilson threw the ball at a 65-degree angle. I calculated the distance from where Russell Wilson threw the ball and where Tyler caught the ball. But pictures show Tyler Lockett catching the ball on the 25-yard line and Russell Wilson throwing the ball at the Seahawk 25-yard line. Below are the variables for the initial velocity formula. V subscript 0 equals initial velocity, r equals 50 yards, g equals 32 feet per second squared, and theta equals 65 degrees. Plugging in our variables, I found that v subscript 0 equals 79.15 feet per second squared. Score! We found initial velocity. V subscript 0 equals 79 feet per second squared. What else do we need? First, we need to find the initial height of the football. It's the starting value of the parabola. This is where the graph will intercept the axis. Russell Wilson is 5'11" and Tyler Lockett is 5'10". For this sound problem, we decided that the ball was thrown and caught at the same height, which we set at 6 feet. Touchdown! We found initial velocity and initial height. Now we can solve the sample problem, shown below. We need to find the axis of symmetry next, because it is the x-axis of the vertex. Question 1. What is the axis of symmetry? Negative b divided by 2a, which is negative 79.15 divided by 32, which equals negative 2.473. Here is the axis of symmetry graphed and shown in red. It is 2.473 seconds. We need to find the maximum height. This will tell us the highest point on the parabola. Here is my work for the maximum height, which turned out to be 103.886. Here is the maximum height shown in red, which is the point is 0, 103.886. Here's the vertex. Axis of symmetry and maximum height combined to make the vertex. The vertex is 2.473, 103.886. Here is the vertex shown in red and graph. The next step is to find the max time. This will show us how long the ball was in the air before coming safely into the hands of Tyler Lockett. This shows the x-coordinate of the parabola's endpoint. Here is my work for the max time, how I solved it. And here is the max time graphed on the graph, 4.947, 6. We are almost ready to draw the parabola, but first we need to find some midpoints to make the parabola the correct arc. I chose 50 feet to solve as the height to find the 2 times the ball crossed that height going up and coming down. Here is how I solved for the new points on the parabola. 50 is the feet we're solving for. Here is the answer to the previous slide of 50 feet. And here are the 2 points, 0.638, 50 and 4.308, 50. We made it. The last building block we need to place is to find the parabola roots, which will anchor it for us, thus showing us the final graph that we have been creating. Throughout this presentation, these are the x-intercept points, which are two real number solutions. Here is how I solve for the parabola roots. Well, for the left and right. Here is the parabola roots graphed on the graph. And here is the final graph that we have worked on throughout this presentation. And to reflect on this, before I thought about starting this project, I never knew that football had a meaningful connection with math and projectile motion. I thoroughly enjoyed creating this project, with it still being related to sports, one of my favorite events to watch in my free time. I learned a lot about angles and how receptions are received and practiced. The project definitely helped in my understanding of projectile motion. It was a great way to do a school project while also making it fun. Maybe next time I can calculate the time it took Tyler Lockett to do this flip into the end zone.